Hello, and welcome to our astronomy course. Today we have lecture number 15. It's called Asteroids, and this is a final lecture of Module B. Okay, so let's start. Space pirates lurk in the asteroid belt in science fiction. But astronomers have found that there isn't much in the asteroid belt for a pirate to stand on. Hundreds of thousands of asteroids are known, but most are quite small. Movies and TV have created a common misconception that flying through the asteroid belt is a hair-raising plunge requiring constant dodging left and right. The asteroid belt between Mars and Jupiter is mostly empty space. In fact, if you were standing on an asteroid, it would be many months of years between sightings of other asteroids. Asteroids are distant objects and too small to study in detail with Earth-based telescopes. Astronomers, nevertheless, have learned a surprising amount about these little worlds. And spacecraft plus space telescope have provided a few close-ups. Notice 4 important points during study asteroids. First, most asteroids are irregular in shape and battered by impact cratering. Many asteroids seem to be rubble piles or broken fragments. Second, some asteroids are double objects or have small moons in orbit around them. And this is further evidence of collision among the asteroids. Third, a few larger asteroids show signs of geological activity that happened on their surfaces when those asteroids were young. And fourth, asteroids can be classified by their albedo, color, and spectra to reveal clues to their composition. This also allows them to be compared to the meteorites in labs on Earth. Before you continue, you should know that not all asteroids lie in the asteroid belt. Many asteroids, perhaps as many as half the number in the main belt, travel in Jupiter's orbit ahead of and behind the planet. These are called Trojan asteroids because the largest ones are named after the heroes of the Trojan War. Also, a few thousand objects larger than 1 kilometer follow orbits that cross Earth's orbit. A few searchers are under the way to locate these new Earth objects, NEO. For example, Loneal Global Observatory Near Earth Object Search is searching for the entire sky once a month. And these searches should be able to locate all the largest in NEOs by 12 years ago. Astronomers are searching for these asteroids to understand asteroids better, but also because such asteroids can collide with Earth. Also, such collisions occur very rarely, and a single impact could cause planet-wide devastation. We will learn about such impacts on Earth later in our lecture. Okay? An old hypothesis proposed that asteroids are the remains of a planet that exploded. Planet-shattering death rays may make for exciting science fiction movies. But planets do not explode. The gravitational field of a planet holds the mass so tightly and completely disrupting the planet would take tremendous energy. In addition, the present day total mass of the asteroid is only about 1/20th the mass of the moon, hardly enough to be the remains of the planet, right? Astronomers have evidence that the asteroids are the remains of the material lying from 2 to 4 astronomical units from the Sun that was unable to form a planet because of the gravitational influence of Jupiter, the next planet outward. Over the 4.6 billion years history of the solar system, most of the objects originally in the asteroid belt collided and fragmented and were perturbed by the gravity of Jupiter and other planets into orbits that collided with planets or caused some asteroids to leave the solar system. The present-day asteroids are a very minor remnant of the original population of planetimals in that zone, mostly fragmented by collisions with one another. Rocky S-type asteroids are believed to be fragments from the crust and mantle, and M-types from the metallic core of differentiated asteroids. C-type asteroids, which appear to have plentiful carbon compounds, are more common in the outer asteroid belt. It is cooler there, and the condensation sequence predicts that carbonaceous materials would form them more easily than the inner belt. As we saw in the case of Vesta, a few large asteroids may have been geologically active, with lava flowing on their surfaces when they were young. Perhaps they incorporated short-lived radioactive elements such as aluminum-26. Those radioactive elements were produced by a supernova explosion that might also have been the trigger for the information of the sun and planets, while feeding the young solar system with its nuclear synthesis products. Not all large asteroids have been active. For example, Ceres, 900 kilometers in diameter, is almost twice as big as Vesta, but it shows no spectroscopic sign of past activity and evidently has an ice-rich mantle. Also, there are still mysteries to solve. You can understand the composition of the material. They are fragments of planetimals, some of which developed molten cores differentiated, may have had lava flows on their surfaces, and then cooled slowly. The largest asteroids astronomers see today may be nearly unbroken planetimals, but the rest are fragments produced by 4.6 billion years of collision. What is the evidence that asteroids have been fragmented? First, your argument might note that the solar nebula theory predicts that planetimals collided and either stuck together or fragmented. This is suggestive, but it is not evident. A theory can never be used as evidence to support some other theory or hypothesis. Evidence means observations or the results of the experiment. So your argument must cite observations, right? The spacecraft photographs of asteroids show irregularly shaped little boards heavily scarred by impact craters. In fact, radar images show what may be pairs of bodies split apart, but still in a contact, and images of AIDA reveal a small satellite, ductile. Other asteroids with moons have been found. These double asteroids and asteroids with moons probably reveal the results of fragmenting collisions between asteroids. Furthermore, meteorites appear to have come from the asteroid belt astronomically recently. So fragmentation must be a continuing process there. Now build an argument to combine what you know of meteorites with your experience with asteroids. What evidence could you cite to show what the first planet's animals were like? Of all the fossils left behind by the solar nebula, comets are the most beautiful. Asteroids are dark, rocky bored, and meteors are fleeting specks on fire in Earth's atmosphere. But comets move with the grace and beauty of a great ship of sea, as you can see in this slide. As always, you can begin your study of a new kind of object by summarizing its observational properties. What do comets look like, and how do they behave? First of all, comets have two types of tails shaped by the solar wind and solar radiation, type 1 for gas, and type 2 dust. The two types of tails show that the nucleus contains water ice and other frozen compounds, plus rocky material, mostly in the form of dust. Comet tails point away from the sun no matter in what direction the comet is moving. Comet heads are called comets. Second, dust in comets not only produces very visible dust stains, but spreads throughout the solar system. Third, there is evidence that some comets' nuclei are fragile and can break into pieces. And astronomers recently commented that the nuclei of comets can be as fragile as marine in lemon marine pie. Okay? The nuclei of comets are quite small and cannot be studied in details with Earth-based telescopes. Nevertheless, astronomers are beginning to understand the geology of these interesting bodies. Comet nuclei contain ices of water and other volatile compounds such as carbon dioxide, carbon monoxide, methane, ammonia, and so on. These ices are the kinds of compounds that should have condensed from the outer solar nebula, which makes astronomers think that comets are ancient samples of gases and dust from which the planets form. 5 spacecraft flew past the nucleus of comet Halley when it visited the inner solar system in 1985 and 1986. Since then, spacecraft have visited the nucleus of the comet Farley, comet Wild 2, better pronounced Wild 2, and comet Temple 1. Images show that comet nuclei are irregular in shape and very dark, with jets of gas and dust spewing from the active regions on the nucleus. In general, these nuclei are darker than a lump of coal, which suggests their composition is like the carbon-rich carbonaceous chondrite meteorite. Interestingly, samples of dust from the tail of comet Wild 2 returned to the Earth by the Stardust probe include chondrule-like particles. Another similarity to carbonaceous chondrite meteorite. This is unexpected evidence that when comets form, they somehow included material from very hot, as well as cold, parts of the solar nebula. Comets, like asteroids, show that the early history of the solar system was cold. From the gravitational influence of a nucleus on a passing spacecraft, astronomers can find the mass and density of the nucleus. Comet nuclei appear to have densities of 0.1 up to 0.25 gram per cubic centimeter, much less than the density of the ice. Okay? The shapes and rough densities of comet nuclei suggest that they are not solid objects. They have been described as dirty snowballs or icy mud balls, but that is misleading. The evidence leads astronomers to conclude that the most comet nuclei are not solid balls of ice, but must be fluffy mixtures of ices and dust with significant amounts of empty space. On the other hand, one comet nucleus, that of comet Wild 2, has cliffs, pinnacles, and other features that show the material has enough strength to stand against the weak gravity of the comet. Photographs of the comas of comets often show jets springing from the nucleus and being swept back by the pressure of sunlight and by the solar wind to form one or more tails. The jets originate from the active regions that may be like volcanic faults or vents. As the rotation of a comet nucleus carries an active region into sunlight, it begins emitting gas and dust. And as the active region rotates into darkness, it shuts down. Also, comet nuclei seem to have porous crust of dark material. The ice and rock are not uniformly mixed throughout the interior. Breaks in the crust can expose pockets of highly volatile ices and cause sudden bursts of gas production. The nuclei of comets are only a few kilometers in diameter. Each time they round the sun, they lose many millions of tons of ices, so the nuclei shrink until there is nothing left but dust drops. A comet may last only 100 to 1,000 orbits around the sun before it has lost all its ice. The comets seen in our skies can't have survived 4.6 billion years since the formation of the solar star system. So there must be a continuous supply of a new comet. Where do they come from? family relationships among the comets provide clues to their origin. Most comets have long elliptical orbits with periods greater than 200 years. These are known as the long period comets. Their orbits are randomly inclined at all angles to the main plane of the solar system. Approximately equal number of long period comets circle the Sun in the retrograde direction as in the prograde direction. You know, the direction in which the planets orbit. Okay? Nice. In contrast, about 100 or so of the 600 well-studied comets have orbits with period less than 200 years. These short period comets follow orbits that lie within 30 degrees of the plane of the solar system, and most revolve around the Sun in the propagate direction. In the 1950s, Dutch astronomers Jan Oort proposed that the long period comets are objects that fall into their inner solar system from a spherical cloud of several trillion icy bodies, evidently expanding from about 10,000 to as much as 100,000 astronomical units from the Sun, later named the Oort cloud. Far from the Sun, they are very cold, lack comas and tails, and are even invisible. The gravitational influence of occasional passing stars could perturb a few of these objects towards the inner solar system, where the heat of the Sun warms their eyes and transforms them into comets. Because the Oort cloud is spherical, these long period comets arrive in our neighborhood from random directions. Some of the short period comets, including comet Halley, whose orbit is retrograde, appear to have originated in the Oort cloud, and probably had their original long elliptical orbits altered by a close encounter with Jupiter or another planet. Many of the short period comets, however, cannot have begun in the Oort cloud. Detailed calculations show that interactions with a planet can't easily redirect objects from the Oort cloud into the orbit that those comets occupy. Rather, those comets must have originated in the Kuiper belt. The Kuiper belt objects that have been found are much bigger than ordinary comet nuclei. But astronomers estimate the Kuiper belt holds as many as 100 million smaller objects. When a Kuiper belt object is perturbed into the inner solar system, it can interact with planets and have its orbit shortened into that of a short period comet. The Kuiper belt object evidently formed as icy planetesimal in the outer solar nebula, not much farther from the Sun than the outer planet. The objects in the Oort cloud lie much farther from the Sun, but they can't have formed out there. The solar nebula would have had too low a density at such great distance. Also, you would expect objects that form from the nebula to be confined to a disk and not be distributed spherically. Astronomers think the evidence points towards the region among the Jovian planets as the original source of objects now in the Oort cloud. As the Jovian planets grew more massive, they swept up some of the local planetesimal, but ejected others to form the Oort cloud. Next lecture, we will be seeing your presentation. Okay, are you ready? And do you satisfied from today's class? Do you have any questions or propositions? So, for now, I hope you enjoyed this lecture, and I'm looking forward to see you next time for the astronomy part. Bye.